Welcome to this keynote lesson about wearable training-less brain-computer interfaces in augmented reality-based health 4.0. I am Pasquale Arpaia from the University of Naples Federico II. I am the director of AREBLab, Augmented Reality for Health Monitoring Laboratory at the University of Naples Federico II. I am also the director of IMPALAB, Instrumentation and Measurement for Particle Accelerator Laboratory at CERN, in cooperation with Federico II of Naples. I am also a researcher in brain-computer interfaces, or better, instrumentation and measurement for brain-computer interfaces, and instrumentation and measurement for augmented reality. Both of them, these technologies, are applied in health applications. The future could be this one.
Initiate Project 2571. Initiate.
To think quickly about the evolution of the computer, and then let's go to the evolution of biomedical instrumentation or instrumentation for biomedical application. Yesterday, we started during the Second World War by an electromechanical large size computer, up to today to the new technologies, and tomorrow to a new scenario. So let's see from Turing Ultra to IoE, Internet of Everything, brain glasses. Line of this presentation, I will go through augmented reality technologies and instrumentation measurement for AR. And I show you how the sensor technology will change from Internet of Things to Internet of Nano Things. Then I'll show you the brain-computer interface technology, the instrumentation for brain-computer interface, and our application of last generation. Then we will show you the Internet of Everything brain glasses developed at Naples University in RM Lab and in cooperation with CERN, then I'll give you some hints and a vision of health 4.0. So the new monitoring approach for health, and finally, a case study at RM Lab of Federico II University. Always, history is written by winners. You can see at the left side of this slide a very bad man that left to destroy, during the Second World War, a town, Coventry, in order to show his technology, or to not show, to hide his technology to these other bad people at the right side of the slide. Why? Germans during the Second World War were really convinced that their Enigma machine, that was an electromechanical technology-based machine for encrypting messages during the military operation, was completely unattackable. But Alan Turing, a young nerd engineer, created a first computer, an electromechanical size of about a room computer named Ultra for decrypting from the UK side. Then we have to say that wars are lost won by intelligence services. Intelligence is one of the most important mankind attributes. Computer evolved. As an example, in 1969, the Apollo 11 mission for moon landing was based on a NASA IBM computer, larger than several rooms that you can see in the pictures. And it was programmed by punch cards. I programmed in my engineering studies, computer science examination, programmed by punch cards. It was a computer input, and the results were taped on punched tape. It was the computer output. And this was the logo of the IBM at that moment. But Steve Jobs, in 1917, created a new concept of a PC, well known to us because it's a personal computer, where we can see that the computer input changed dramatically, and also the computer output was changed in the same way. We can say from 1917 to today, we can see that the keyboard is still used, but it's not really true, because we have a new computer input, a touch screen on our smartphone tablet, and also the output is a little bit different from the original version of the personal computer, because we have smartphone and tablet screens. We have to see and to say that also the computer input is evolved now by a vocal assistant like Siri or like Alexa, the only woman who listens to me in my home. Let's go to the second part of my presentation, and let's go to see the augmented reality technology and our chances as a biomedical instrumentation and measurement researcher with this new technology of augmented reality. Let's define augmented reality as a physical world plus a digital information. You can see in these pictures some smart glasses on the top, and on the bottom some typical displays on smartphones. A quite bit different is mixed reality, link between physical and digital objects where they are potentially indistinguishable. So the computer evolves again by viewers for virtual reality. The computer input is a touchpad controller, and the computer output is on the viewer screen in immersive speakers or haptics I/O. We have smart glasses, and where the computer output is on the glasses and the computer input is on the touchpad. We exploited such technology of augmented reality at the University of Napoli Federico II in our IMP lab for a project where we created an avatar-assisted augmented reality rehabilitation after stroke in cooperation with some industries. The innovation was that our avatar is an Excel game that self-adapts by measuring the patient's actual impairment. So it provides a closed-loop feedback on the rehabilitation progress based on the measurement. This means that the user, the patient, will not bored by the rehabilitation, will not bored by the Excel game, because the Excel game difficulty is adapted, is tuned in real time on the progress of the patient. So the patient is always tracked in the rehabilitation. Augmented reality has several applications in health. As an example, surgery. It is used for displaying in maxillofacial application inferior alveolar nerve bundles. The first step is that actual and virtual reality are mixed for a see-through experience. And when the mandible is exposed, virtual images and actual bone are overlaid in a three-dimensional view. This is obviously done in order to help support the surgeon. But such a overlaid must be really accurate. So a challenging pedagogical problem of fiducializations arises. During the surgery, the surgeon is driven by stereotomy lines projected by augmented reality. Also in this case, embryological challenging problem of fiducialization arises. This means that there is space of research of a clear need, a clear requirement for instrumentation and measurement technology for metrological applications. Another straightforward application is for endoscopic sinus surgery, as you can see by this slide. We tried to face such a challenge in RM lab by developing a robust ultrasonic hidden goniometer, robust against the typical magnetic interference created by instruments in operating rooms. You can see that we have two capacitive ultrasonic transducers converting mechanical rotation into corresponding time-delayed electrical sine waves. The prototyped goniometer, and you can see the architecture in the picture, achieves the same readability level, less than 36 milliradian, of a magnetometer-based heating. Another important application that we carried out at RM Lab was for the Augmented Reality for Surgery research project, carried out also in this case with industrial partners. Main objectives were a real-time augmented reality data monitoring for supporting the surgery and embedded artificial intelligence for real-time prognostics. So you can see the operating room instrumentation, which is interfaced to the computer of the augmented reality. And the patient health record information is processed in real time, along with real-time instruments data of the operating room in order to prognose the quality of the surgery. The system works like a hands-free augmented reality system for access to patient medical record, monitoring patients' vital parameters, video streaming from teleoperation robot or endoscope, and predict the surgery success by a machine learning-based predicting algorithm. The systems the application is organized like a spherical environment surrounding the surgeon help. Moreover, the surgeon help can navigate through the menus by a brain-computer interface that I'm going to show in next slides. So the surgeon help can access to vital parameters monitoring, like you can see in the picture at the right, where on the left you can see the picture of the concept architecture of the system. At the end, the video streaming and the predictive algorithm are fused. Namely, the algorithm can access as input the endoscope streaming and analyze in real time the video images in order to have a prediction of the quality of the surgery. Let's go through the next hot topic of this keynote lesson. Namely, I'm going to show you how the Internet of Things is going to changing to Internet Nano Things, and namely the application for health, for biomedical instrumentation engineers. We said that augmented reality is the superposition of physical world plus digital information. Well, the digital information usually arises from Internet of Things wireless sensor networks. Internet of Things means Internet of Objects, where all the devices such as computers, smartphones, smart glasses, or transducers are connected. We are speaking about physical objects. As an example, popular example, I can remotely know the temperature of my apartment by an SMS from a smart transducer. But I can also modify the temperature by just sending a command from my smartphone to the boiler. So there is a wireless sensor network connected to internet. Few years ago, Cisco company launched the concept of Internet of Everything, where not only physical entities are connected, but also not physical entities like Google, Facebook, Dropbox. In the previous example of the apartment temperature, Internet of Everything integrates interchangeably and seamlessly not only the device but also the border user interface, dimensional data, and so on. So, as an example, in a railways system, not only physical railways and exchanges, but also services and people, trains, ticket offices, traveling staff, users, weather condition, and so on, are integrated. This is a really big business because you can see the investment that are ongoing in Internet of Everything technologies. You can see that the brick even point was already passed because now we have more connected device than the world population. Within this year, we will have 37 billion of new things connected. This is really an important chance for us because we are thinking and we are speaking about sensor and transducers connected, wireless sensor networks. Also, health. And this is a big chance for MeMeA researchers. You can see what is happening to the global IoT in a healthcare market. And the forecast is that we will have about 400 millions of US dollars invested for 2025. Also here, the sensor investment in red for health. This is a really big chance for MeMeA research. But like all the technology impact, we can see that also the Internet of Everything is going to saturate the penetration on the market. Because we are here, like the red arrows points out. What is happening now? Internet of Nanothings. We have nanosensors embedded over the world, transmitting info under request. And we can have also nanosensors embedded in our body. And they cannot exploit or they do not need for wireless connection because inside the body they exploit molecular communications. What is molecular communications? This means that, as you well know, we are made of water, or to be more precise, we are made by saline water, conductive water, namely an electrochemical solution, which is conductive. So we can send data directly by ourselves, then to a gateway and to internet. So we are speaking about an Internet of Nanothings, where we have several sensors in a future or in a current research application, several nanosensors embedded in our body and transmitting info under request in real time. May we speak about a further sense that we're going to have? Because all the data the digital data of such of nanosensors embedded in our environment creates a digital measurement data that we are going to exploit in real time. For this exploitation, we need for new computer interface. This is the reason for which I think about a brain-computer interface, where computer is accessed directly by our thoughts, by the brain, without the mediation of a keyboard. This is a popular dream of the human mankind. This was an amazing sketch movie about this dream of the man of acting under reality without any mediation, only by thought. This was really made in practice by theory, the theory of a cyber-physical system. It is an engineering theory, an information theory. What is a cyber-physical system? It is a computer system able to interact continuously with the physical world through elements, each with the computational capacity, communication, as well as measurement and control. But a cyber-physical system needs for an interface, for collaborating with man, machine, and tool. And this is called a cyber-physical interface. You can see the picture, the Ghost of Shell movie, a picture of the movie where you can see that the person, Scarlett Johansson, is integrated, wired with the computer. In this cyber-physical interface, we have two really important concepts. One is artificial computing and communication structures. The prefix is cyber. And the other word is the physical suffix, which means measurement system. So the interactions is between measurement data and computer and man is mediated by this interface. In engineering research, the most promising advanced cyber-physical man interface is the brain-computer interface. Brain-computer interface, that I am going to call BCI, allows a direct connection between brain and an electronic device without using muscles and nerves, but directly by thought, which is the most important straightforward application. Well, to restore lost feature functionalities of the human body, because the robotic arm can be actuated directly by brain thoughts, by measuring, and I stress the word measuring, by measuring the electrical neural activity of the subject. This is something that we are capable to do, measure the brain activity. Or I have to say that the market of BCI is really enthusiastic. You can see that the global, in this year, market will be about 1.47 billion of USD. And you can see here a share of the market by type, by invasive, non-invasive, and partially invasive. And we can see that the highest revenue will be generated in North America region in this year. And you can see here a global share of the market by application. And we can see that healthcare is the most promising segment. Last but not least, you can see in this picture where the top impacting factors are. And you can see how this situation is changing from the two different nuances of blue. What is the brain-computer interfaces? We have on the left brain signals, electrical brain signals, which are acquired by a signal acquisition, a data acquisition. Then we have a further step of signal processing, where the most significant features of the signals are extracted and then are translated in order to generate a control through a BCI application, which gives a feedback to the human. So this is the main tool for the realization of the human dream of moving objects by our thought, because I can have a suitable activity, electrical activity in my brain, which is measured and then suitably processed in order to actuate a machine, a tool for moving the object. You can see here a typical example of application of a brain-computer interface for a person which is not capable of moving his, her fingers over the keyboard.
Allows a user to spell words using a keyboard which is on a screen and which flashes. And the fact that it flashes induces certain brain activities when the letter that the person wants to spell is flashed.
We ask the user to concentrate on the number.
Allows a user to spell words using a keyboard which is on a screen and which flashes. And the fact that it flashes induces certain brain activities when the letter that the person wants to spell is flashed.
We ask the user to concentrate on the number.
The same concept is exploited here for moving a wheelchair.
The demo. The subject is looking at the 10 Hz flicker box, and this is making the wheelchair move forward. Now she is focusing on the 12 Hz flicker, which makes it turn right, and so on. Now, in order to stop the wheelchair, the subject has to clench by biting the teeth. Thank you for your time and enjoy the rest of the video.
Now let's see some applications of brain-computer interface, or the most important ones, in communication, for rehabilitation and restoring of lost function, or in entertainment, for gaming by virtual reality, augmented reality, or thematics. But daily applications require light, wearable, and efficient BCI system. Why a measurement research for brain-computer interface? You can see here in such a picture a typical brain-computer interface based on steady state visually evoked potential, SSVEP. You can see here that it is based mainly on a measurement unit where we have some sensing activity, then a data acquisition activity, a data processing activity, and the loop is going to be closed by a feedback unit and a control unit. This is again a topical architecture for implementing the mankind dream of moving objects by thought. You can see here the instrument that we developed at the RM Lab by using only off-the-shelf components and low-cost devices with an optimized metrological and real-time performance. So we have trainingless brain-computer interfaces by differential single-channel digitizer and dry active electrodes. We have here also a different research activity that we carried out at RM Lab for AVTIA, Advanced Virtual Adaptive Technology eHealth Research Project. And you can see also the industrial partners. Our main goal is a measurement of engagement rate of a person. And we based this measurement on EEG. This was carried out for self-adaptive neuromotor rehabilitation. Engagement, the measurement of engagement for us, is a combined result of attention measurement and emotion measurement. As you can see in this table, you will have emotive valence on the column, positive and negative, versus motor attention levels, high, medium, medium-low, and low. So you can have here the engagement measurement. You will have here in these cells high and medium engagement. On the other side, you will have boredom and rejection. This seems to be a successful approach in our current research. You can see here sketched in this slide the system, the conceptual architecture. We have EEG, electroencephalographical data acquisition, for motor attention measurement and emotive valence recognition in order to fuse such feature extracted, selected, and classified by artificial neural network or support vector machines in order to measure the engagement rate of the subject. Another important application of such a measurement system we carried out at RM Lab was worker stress measurement, where we have a highly wearable trainingless single-channel instrument which is going to detect human stress in real time by measuring EEG signals. Main features are a single-channel differential measurement, a frontal asymmetry, and meteorological characterization on human subjects. You can see here the very easy and straightforward architecture of the system. Features are extracted directly from time domain, and a principal component analysis can be exploited for classifying the different features. We used 4 standard machine learning classifiers in order to reach, alternatively, more than 90% activity. You can see the random forest 99 and the artificial neural network based one 99 with the relative, the absolute uncertainty band. You can see here another movie highlighting our research trend. We do not want to stimulate the user by a flickering icon in order to actuate the brain-computer interface. We would like to exploit directly the measurement of the thoughts, which is called technically the natural potentials, because we have visually evoked potentials versus natural potentials. So what is happening is that I am thinking about a movement, then the corresponding neural activity is recorded, detected, classified, and then actuated in real time. You can see here in this movie the headset, which is the subject, is in this moment wearing. And you can see that it's not so much wearable because the subject is wearing an headset, which is boring because it is of silicon and exploits a lot of wet electrons. This means that your hair will be obviously full of moisture. Let's see the movie. Here you can see that the subject is capable of actuating some movements of the ball in order to move through the side of the screen, which is flashing. So I want, in this moment, to send the ball at my right. This is a really interesting application, and this is a brilliant implementation. But which is our future work, is that to use dry electrodes with a reduced number of measurement points with a real-time engagement assessment. This is what we call the reduced number of measurement points, EEG, electroencephalography low density. Advantages main are wearable and wireless system for acquiring EEG signals in direct environment. Let's go through now another important realization of our labs, the IoE, Internet of Everything, brain glasses. In such a slide, our design was driven by the following requirements: high portability and wearability, low cost and components off the shelf, 1 millisecond of temporal resolution, and 1 centimeter of spatial resolution. Using the most and well-settled technology for brain-computer interface, the steady-state visual evoked potential signal, because they have high signal-to-noise ratio independent from cognitive processes, which are simultaneously worked by the human brain, and the visual stimulation. So we have high portability, low cost, high performance, meteorological performance, independent from brain thoughts and noise, but we need it for a visual stimulation. Let's see now the typical architecture of an augmented reality platform for monitoring purposes, exploiting a wireless sensor network. You can see here that we have a touchpad, which is the input interface of the microcomputer-based augmented reality system. And then you have the output interface, which is typically smart glasses. So the user can have superimposed directly on his real vision the data of the wireless sensor network. This is a monitoring system. In such a slide, you can here see the integration of the former, of the latter platform with the brain-computer interface. Which is new here is that you have, as an input interface, a brain-computer interface, which is constituted by EEG transducer, a signal acquisition board, and some electrodes. Then, on the microcomputer, you have the process of feature extraction and classification, and then the output interface of the AR glasses. You need, for a visual stimuli, that is projected on the AR glasses, and you have the BCI on the other side. Are the system components that we used in RM Lab. A AR glasses and default controller from Epson, Movirio, BT2 or BT350, and Alimex electrodes and acquisition board. You can see here the electrodes placement. We have a differential measurement, and we have a reference electrode, a measurement electrode, and a ground. Here, in such a movie, our last wireless prototype, where you can see the glasses, the electrodes of the BCI, and the system as a whole with his high wearability. Let's go now to illustrate how such technologies can be exploited for radically and dramatically changing the monitoring system architecture in a new monitoring approach. We are used in industry environment monitoring system based on sensor network and virtual instrumentation, like LabVIEW as an example application. But this architecture is going to change owing to new technologies that I just illustrated you. Let's see a first example in diagnostics, industrial diagnostics. The technician looks at the system, which is possibly affected by an anomaly, by smart glasses. On the lenses, a suitable interactive menu is projected with a schematic explosion of the parts, with relative data on the probability of defects and faults. But when you are looking at the specific part of the plant you are inspecting, the needed information is displayed. And this is a typical AR-based inspection without any monitoring data. Our technology, you can have your glasses, which is the I/O interface of our monitoring system. Then you have the electrodes. Then you have the data acquisition board and the Air platform microprocessor. Wireless transducers are going to connect to such a monitoring system based on brain-computer interface, low EEG density, and highly wearable. You can see here, unfortunately in Italian, what is the user experience, because you see on the left eye corner the transducer 1 icon, which is flickering, and on the bottom right corner a second transducer which is flickering but at a different frequency. So according to which of the two squares you are watching, the brain-computer interface will select the user choice. You can see the two different icons flickering in this picture. You can see humidity and temperature, and the user is watching on the right, and he will have the temperature displayed on his glasses. You can see here what we carried out in cooperation with CERN in our IMPALAB, Instrumentation and Measurement for Particle Accelerator Lab of Federico II, in cooperation with CERN. You can see one of our PhD students on the left, which is wearing our IOE brain glasses for actuating the robot in order to pick up the box. After picking up the box, the robot is driven to give back the box to the person. And you can see the final laughing of the PhD students of IMPALAB. Now we are going to see, which is called Health 4.0, which is really important for instrumentation and measurement application in the field of biomedical engineering, of general medical application. Now, Industry 4.0, which is launched in 2014 by Angela Merkel, and you can see also in this table the well-known situation that the Industrial Revolution are becoming more and more rapid. So you can see that in the first one you have a duration of several years. We can see about a 1 century, and then you will have that from the third to the fourth, it's only 20 years or even less, 15 years. You can see also here the most important enabling technology. You can see that for Industry 4.0, from engineering the cyber physical systems are considered the most important technological pillar of such a revolution. From Augmented solution, you can also see that 9 technologies that are transforming industrial production in Industry 4.0 are augmented reality and industrial Internet of Things. What is not really well known like Industry 4.0 is Health 4.0. So there are some important features transferable to health from Industry 4.0 that have brought us to speak about Health 4.0. Most important ones are interoperability, virtualization, decentralization, real time, and focus on service, and not only on product. Health 4.0 global investment has a very interesting trend. You can see here that in this year we will reach the level of 233 billions of US dollars. So this is a very important field where we have to address our research, because we will have a lot of money in this. You can also give a look on a breakdown of such investments over the last years. And you can see that wireless health will have a very interesting and promising trend. And also telehealth. Most important keywords of Health 4.0 are clinical decision support system, Hospital 4.0, where the hospital is no more a building, a physical place, but is something of non-physical, which has also connection on territory because patients are at home. Also Pharma 4.0 for all the drugs, technologies, and system medicine. But let's go to conclude our presentation by a case study at RM Lab of Federico II of such a monitoring system. You can see in such a picture our augmented reality for healthcare, integrating augmented reality and BCI for rehabilitation. Our main aim is the enhancement of cognitive, social, and motor skills for children with autism spectrum disorder or attention disorder. The system is able to control a robot by means of brain signals by analyzing SSVEP signal and eye blink voluntary artifacts. And the augmented reality smart glasses are used as a generator of stimuli as a computer for hosting the driving system. What's happened is that the children is really involved because the children is autistic or has attention disorders, but is not stupid. So he really realized that during the therapy with the robot, he is driving the robot by his thoughts. So he's really involved. Our preliminary results showed that the therapy results are better than 200% with respect to traditional robot interaction therapy. You can see here the robot, the movements, which are driven by our PhD student Isabella in our lab. You can see here a small promo movie that we realized in RM Lab in order to highlight our technology for industrial partners or for finding potential partners in research projects.
Brain-controlled robot. The system here described is a brain-computer interface developed at University of Naples Federico II. Such a system is able to control a robot by means of brain signals by analyzing steady-state visual evoked potentials from onboard SSVP and eye-blink artifacts. As for SSVP signals, augmented reality smart glasses are used as generator of stimuli. The user, keeping a focus around one stimulus out of two, make the system send the desired command to the robot. Moreover, the number of available commands is increased using the eye blink detection. In this application, the user can choose to move the robot to the left or to the right, simply by observing the associated stimulus. Meanwhile, the start and stop of the robot is given by an eye blink. The radio technology chosen to make the BCI communicate with the robot is the Wi-Fi. After an offline analysis, it has been observed that the success rate of the system can reach the 70% with a latency of about 1 second. Brain
So in conclusions, let's have to give a look to the cons, the pros of our technology. Main pros are the technology is wearable and easy to use, can be built with off-the-shelf components, and allows hands-free operation. Which are the main drawbacks we are facing now? The brain classification is critical, but the algorithm must have a lower computational burden. And a more advanced prototype could enhance electrodes adherence and wearability. So let's conclude my presentation by highlighting that learning is your best investment. So thank you for your attention.